Okay, so as you all know, I'm doing a presentation here on the physics of parkour. Okay, so first an introduction to parkour for the people who are the physicists in the room. Parkour, abbreviated PK, now started in France, is a method of overcoming obstacles using many facets of human movement. Inspired by an action method created in 1905 by, I can't say that guy's name. David Bell, who started with being founder of parkour, he was inspired by the method it's still used today. It's used by the French military to overcome obstacle courses for training drills. The obstacle courses are called Parkour. Thus went into the name Parkour. Bell and a group of his friends, called the Young Cloudy, began to develop and adapt the idea of overcoming obstacles to the unique architecture of urban environments. So the techniques are somewhat complex. The overall goal is very simple. A tracer, also get used to that because you're going to hear it a million times, parkour practitioner aims to move through an environment containing natural or artificial obstacles as quickly, efficiently, and safely as they possibly can. So, focus of the research. My goal of this research is to analyze and understand the underlying kinematics and dynamics of the physical discipline of parkour in its many physical dimensions. I aim to understand both the mechanical breakdown of each movement as well as the purpose for which they are performed and the importance of the method of their performance. The way that people tend to perform them in parkour, that it's been being developed and people have a very efficient method of doing things, and I wanted to figure out why people do things the way that they do. I directed this presentation and my research to be able to inform both the physics community about parkour as well as the parkour community about physics. Okay, so some theory. Parkour people, it's a lot of numbers. The physics people, it's really simple. So we have here basic trajectory. This is your y directional trajectory. G is the gravitational constant. So you have your initial height plus the initial velocity in the y direction plus 1/2 the acceleration due to gravity time squared. And then you have your x directional motion here, which is your rotation equals your initial rotation plus the x direction plus initial velocity in the x direction times time. These down here give you an idea of what v naught y and v naught x are, as you see in these two equations. The v naught y is this sine function of the angle that's being used times the total initial velocity. And obviously this will be like that. Fourth theory. Okay. Basic stuff. Force equals mass times acceleration. Also equal to dV over dt. Momentum equals mass times velocity. And J here, which I don't know if I end up using, is the integral of the momentum with respect to time. Okay. Work equals force times distance, but the force has to be parallel to the distance. That's what that little parallel sign is. So the best example of that I would use here is a waiter carrying a tray of objects is not actually doing work on the tray because they're walking forward, because the direction of the force is upward and the distance that's traveled is sideways. So that's not work. Work is the force times the distance as long as they're in the same direction. And then you have potential energy here. Potential energy is based on the height of an object and its mass. So you have mass times gravity times height. And then kinetic energy equals 1/2 mv squared, mass, velocity squared. And apparently I missed out on one of my equations, but by the law of conservation of energy, total kinetic energy equals total energy equals kinetic energy plus potential energy. Okay, got it now. Okay, force of friction equals mu F normal. So basically what this means is your force of friction, which you'll see come up a few times, is equal to a coefficient of friction, which is based on the items that are in contact with each other and how sticky they are. So we'll talk about shoes a bit with that. And the normal force is the force acting, pushing it against the object. Okay, torque. Torque equals the force times the sine theta, so the sine of the angle. And R is the distance between, it's hard to describe without showing the picture, but we'll come across it in the picture. And net torque, I didn't end up using this because it's really difficult to do this, as I found out yesterday. Net torque equals the angular acceleration and the, why am I forgetting words today?
Rotation and inertia.
Thank you. Rotation. Okay, so optimal jump and some switch equations. I don't know how that happened. The optimal jump is a jump which covers maximum distance for a given initial velocity. It's very easy to prove in physics that the optimal jump happens at a 45-degree angle. It's because you want equal amounts of velocity going into your x direction as well as your y direction in order to get your maximum distance. Okay, so into the parkour. The precision jump. From a standing position with feet side by side, the tracer leans forward and leaps, extending the body for maximum power in the direction of the initial velocity. The distance that will be covered by the precision, which you see a step-by-step progression of it, ignoring the landing because that comes later. The distance covered from jumping point to landing point, actually technically it's from center of mass to center of mass, is x equals 2 v naught x, v naught y over g. Okay, so the precision jump. These weren't supposed to be up there at the same time. But it's okay. Alright, so this was one of the things that I came across. A lot of people teach the precision jump as put your feet together and jump from both feet. I discovered / figured out that this is actually a wrong teaching method. It's not a good way to do it. You see this arrow here, which blends in way too well with the picture. This arrow is the direction of force coming out of the legs. Now, if your legs are together, your hips are not the same width as your feet are when they're close to each other. As a result, you're going to actually have a theta here in between this arrow and the leg. That theta will actually result in, back to the equations with the sine theta and cosine theta, where they split up, that will actually result in a loss of energy. So the ideal precision actually happens when the side of your foot is lined up with the side of your hip. It's a little bit wider than what most of us jump with, but I showed mathematically in my paper, so I'll probably put it up here, that the change in force for someone like me is dependent on how far your precision is in the first place, but for me, the change in force is actually approximately 6 inches. And as dresseurs, 6 inches is a big deal. So try it out sometime. You'll actually find it's actually really interesting. It might be slightly awkward at first, but you'll find that you actually gain more power. So now talking about the precision jump physicists out here, the way the precision is executed is the legs are bent, the back is bent, and the arms are swung back and then forward. The arms actually give strictly forward momentum. This is something I didn't expect based on the fact that when we do this sort of movement, we're throwing the arms upward. So I expected that the arms would actually create some upward force. It doesn't. When I did analysis on the motion of the arms as well as doing precisions with my arms at my sides versus having them swinging, the height never changed. So came to the conclusion that it actually only helps you go forward. The body extension and the leg extension, on the other hand, gives something like 96% of your thrust to the jump. One of the odd things that I came across, which I'll also discuss a little bit later, is that despite the fact that dresseurs are always getting their maximum distance, and they know this from practice, I couldn't find many instances where they actually jumped at 45 degrees, and I have some theories as to why they spoke there. That's not supposed to look right. Okay. So, I know what it says behind there, so I'll just say. Arms are swung back and forward for forward momentum, and for the jump, I've already said this. This has something to do with it. Something I've already said. Now, the precision where you change level. This is a more interesting situation. There are 3 ways to traverse a downward lie precision. Now, this equation right here will actually give you the distance traveled when the point where you're landing at is actually lower than the point that you started at. So it's a much more complex equation. So if you think of the idea of jumping from point A to point B on a level surface, and then you go, oh, well, this next surface is a foot down, I'm sure I can make it because even though it's a foot farther, it's a foot down. It's not that simple. It's not a direct linear relationship. This is the relationship between distance and a downward line. There are 3 ways to traverse a downward line precision. There's the optimal angle with minimal power, so that's jumping at a 45-degree angle using the least amount of power you can. You might think that that's actually the most efficient way. It turns out it's not, and I'll explain why in a second. There's the minimal angle with maximal power, so you actually use a smaller angle, kind of like this. This picture's turned sideways, but in this picture I'm jumping at about a 20 to 25-degree angle. So there's minimal angle with maximal power, where you jump harder, but you lower your angle, so you make up for the distance you don't get from the optimal angle by jumping harder. And then there's the maximum angle, maximum power. So there are 2 angles that will get you to the same place that are, if it's not optimal, if you're not using the optimal, there's 2 angles that will get you to the same place. One has more y and gets you to the same place, one has more x and gets you to the same place. It turns out that a tracer will almost always take the minimal angle, maximum power route. And there's a reason behind that. We would expect that the optimal angle with minimal power would be the best thing because you think efficiency, minimal power. But the problem is, when you're going downward, if you take the optimal angle, you're getting more upward force. And because you're getting more upward force, you're going to fall further and harder. So you end up losing safety, which defeats the purpose of the efficiency in the first place. Okay, run-up. What determines the speed of a tracer's run-up? This was a really interesting problem. Trying to figure out what causes us to run at the speed we do. If you ever see a tracer running, they do not run at a full sprint. It is impractical. You'll find that if you try and run at a full sprint, screw up all your technique. So what determines that speed? Obviously, you can't walk into a technique because you don't have the momentum for it. And you can't sprint, as you probably found out by experience. Turns out, there's an equation. So, oddly enough, what determines the speed of the tracer's run-up is Vy naught. Y is in the vertical direction, so that's a little bit unexpected. So Vy naught is equal to the square root of 2gy max, which I just calculated after 2g, doesn't really matter there, but I did really good. The reason for this is when trying to make a jump, the Vy naught is actually your limiting factor. When a traceur is running and jumping, they're limited by their maximum vertical leap. Because your maximum vertical leap is your maximum vertical leap. You cannot make your muscles go stronger or harder. You have a maximum there. Whereas with your run, depending on how slowly you gain power, you can get a lot more forward momentum than you can upward momentum, because that still comes directly from the final impulse of your jump. So, what determines the speed of the tracer's run-up is that equation plus the consideration of the distance that you travel equals 2 v naught x v naught y over g. This is because basically this is a constant because your maximum height is your maximum height. So this is a constant, g is a constant, x is whatever you're jumping to, so it's a constant for the situation. So the only thing that varies here is v naught x, which is your running speed. So it turns out that your running speed, you will influence your running speed depending on how far you have to travel by knowing intuitively how high you can jump. So we come to the stride jump. The stride jump, as well as a properly executed plyo or continuous precision leap. Where's the lights in here? Okay, so I want to explain this, so I'm going to show. The stride jump is quite simple. It's striding. That's a stride. There are two different ways to do a plyo, as far as I understand people's different definitions for a plyo. So a plyo can be a one-footed stride, or continuous precision leap. And by that, I mean you're already moving, and you continue through. Next one, pushing later. So that's what that's referring to. So these are continuous jumps. You're already moving forward while you do the jump. They rely on previous x-directional momentum for the primary source of the x-directional velocity in the jump. So you're not actually jumping too hard in the x direction after running. You actually tend to conserve the momentum that you got from your run-up, rather than trying to jump further forward than you were already running. Most of your jump actually goes into your vertical. Okay. Further gaining x-directional momentum is limited by the speed of the leg. So where the amount of force that you can create with your leg, the amount of power you can create with your leg, determines how high you can jump, the x-directional momentum tends to be limited by how fast you can fire the muscles of your leg, which goes a little bit into biomechanics, which obviously is beyond the scope of this. But just to understand, power limits the upward direction and speed limits the x direction. Bidirectional momentum is limited by the strength of the leg and is provided by the vertical leap height. Precision landing. Precision landing is a two-footed landing coming to a complete stop on the landing target. It's pretty much the exact opposite of the precision jump. We have these two jumps. So what we have here is I asked someone to do a stride precision. So the red line is actually their initial stride, and they followed straight after the stride in a continuous leap into a precision, where they landed over here. Now, what I found from this was that for an optimal landing, which an optimal landing is just like an optimal takeoff, it tends to happen around 45 degrees. For an optimal landing, there's actually an equation that designates where your center of mass crosses the plane of your landing point. So here we have an undershot, and you see the y equals 0.491 meters. Because of this, which I'll explain why because of this, he fell backwards. He didn't complete the precision. On the over, 0.981 meters, he actually fell forward and couldn't complete the precision. And this last one, 0.70, which I was so happy that it was 0.70 because it matched my prediction. 0.70, he landed the precision perfectly, coming in at a 45-degree angle. So what dictates this? The optimal precision landing takes place with a 45-degree angle of incidence and a parabolic of the center of mass intersecting a point square root 2L squared above the landing point. But L equals the measurement from the joint of your knee to the joint of your hip. So you can actually come up with an exact equation for where your center of mass should be when you finish your landing. This is for an optimal landing, so, and I don't know if I discussed that quick. But there are other situations, for instance, if you're coming in at a different angle, you have a different type of landing. Continuum motion versus precision. So the previous graph, you had the continuum motion in the first one, and precision in the second of each curve. So continuum motion is simply the same parabolic as the precision landing. It looks the same. The only difference is the parabolic is actually aimed past the object on purpose, so it would be one of those higher numbers. If you actually end up accidentally aiming if your parabolic actually intersects the point where your optimal landing point would be, you'll actually lose all your power when you land, and you'll get one of those weird stutter stops where you meant to jump from it. So it's the same idea, it's just aiming past the object which the landing is taking place on. The precision landing relies on friction to diminish the x-directional momentum. This frictional damping is replaced with torque for continual motion. So, sorry, I'm going to turn on the lights. So, the way that this works is when a precision landing is executed, the feet are laid down. They're either being pushed against the edge of the wall or they're on top of the wall. Either way, you're creating this damping motion where you stop your x-directional motion using the force of friction underneath your feet. On the other hand, if you want to actually have continual motion, you don't allow that frictional force to stop you, and instead, when your foot hits, the frictional force creates a torque around that foot, which continues your motion through the next step. Vaulting. Vaulting is the act of using the hands and arms in conjunction with a jump to overcome an obstacle. The aims for maximum efficiency, flow, and speed. Flow is a common word used in parkour. Flow is actually a common interpretation of the conservation of momentum, whether or not people actually realize it. That is what flow refers to as the conservation of momentum. Efficiency is defined here to be the minimum height of center of mass while maintaining constraints on speed and safety. So, we have the speed vault. Now, the interesting thing about the speed vault is you actually get a torque in here. So the speed vault is a side leaning vault, and this is what it looks like when I do one. And what you end up having here is the R, which I was saying I would discuss later, is here. It is the distance between the hand that's planted, assuming the hand is straight up and down. It's a bit of a rough thing here. It's the distance between the hand that is planted and the center of mass. And the center of mass is creating a torque by pushing downward, so you get a rotational torque this way. On all of your vaults, as you'll see in a second, on all your vaults the same phenomenon happens. So you jump and you twist your body in some way or another in order to keep your center of mass as low as possible. By placing a hand down, you create this torque. And by creating the torque, when you pick up your hand, your rotational momentum continues. You have rotational inertia. And that's what brings you back to your feet. I use terrible switching. I'll switch out our big roller balls. We have calm, the exact same thing. This isn't shot very well from the side, but you should get the idea. If this was shot from the side, the arms are here, the center of mass is here. So again, you have this torque, it's just on the back end of the body. That's not a dash ball. That's dash ball. So there's dash vault and excuse me, my other dash vault. Yes. Okay. So dash vault, same exact thing. You have the distance R here, and the torque is created here. Interesting vault comparisons. So what I find really interesting here, and I was really surprised to find, is if you look at these two, you'll notice that they're incredibly similar. And in fact, this portion here is mirrored here. This is in fact the, let me make sure I get this right. This is the dash vault and this is the Kong vault. They are identical in the amount of energy used. They're just reflected at this point. Some background. The triangles here represent the center of mass, and this is a graph of the center of mass height versus time. So yeah, very interesting to see if these are the same. The only reason that this has a lot more dots is that this happened to have been shot in 60 frames per second, and this was 30 frames per second. This here is the speed vault. Speed vault has some interesting advantages because of the fact that the way that the speed vault is executed, it can be done better at lower heights, whereas a Kong or a dash requires you to fall to your wrists, which is not exactly good, or to lower yourself in the first place, which is a waste of energy. So the speed vault tends to be the ideal situation for something that's below hip height, where the center of mass actually can stay in the original position it was in as you were running, the original height. And then you turn and go straight back. The speed vault is called the speed vault for a reason. It's because it is the fastest vault that you can execute. Because even at a full sprint, the speed vault still works. Kong and precision require a little bit more of a proper run. Okay, so I'm going to switch over to. That's right. That's really right.
Thank you. I don't have records anymore. Appreciate it. Okay. So, I want to show you a couple of these examples here. If I can get it to work. All right. There it is. Okay. So, we have here the data for the dash vault.
So you can see how this is executed. The person jumps, and at the height of their jump, their hands get placed down, creates a torque as the center of mass continues downward due to gravity, and the arms are holding up the upper body. So you get the torque there. The rotation continues. So right now he's still laying on his butt, but because the rotation continues because of the conservation of the rotational inertia, he comes down onto his feet and continues to roll. And then we have the Kong. The Kong is the one that has the very, very similar graph. So the Kong is the exact opposite. You actually lean forward for this vault instead of backwards. And you see here again, the center of mass is very far behind the upper torso. If his hands didn't hit, you would take a pretty bad fall. By hitting the hands, you, again, in this case, you actually push up slightly, which creates the torque and the rotation. And the feet come through to follow the road.
Last, we have here's the speed vault. Now the speed vault wouldn't normally be done at a height like this. I was just trying to get consistency with my
work surface. But in fact, this is actually more of a situation that we want to use the column because of the fact that he very clearly has to jump pretty hard in order to get the speed ball to cover all this. But you see the legs go to the side, the arm creates some torque so that the legs can rotate back underneath the body. While I'm here, we have the precision. This is very basic precision. Now there's actually a slight downhill line here, so I end up jumping with a lower angle than 45, which honestly most of them end up jumping with lower angle than 45. But you can see how it's executed here using the arms, the body, and the legs all simultaneously. More to demonstrate an extreme example of the downhill decision. This here is a 12-foot gap, which is well beyond my normal max at a level surface, but it's also down by almost 7 feet. So you see the precision actually executes almost horizontally in order to reach the precision point here.
When you're learning to do these things, it looks to me like you're doing the staff, your analysis is of what works, but you learn how to do what works first.
Not exactly. It depends on sort of what generation you are in the parkour world. Some of us older guys didn't really learn how to do what works first. We just started jumping, and then we sort of figured out almost through an evolution of the techniques what actually works.
But I guess you've come to the physics of this after figuring out what works.
Mm-hmm.
Have you changed your jumps because of your analysis?
Yes.
So which jumps have changed?
The precision changes have said that it's taught wrong very often. I also changed the way that I wall run, which is kind of fairly slow. What am I at? Time. So the cat pass is a column performed on an equal level. Makes a downward movement over an obstacle more efficient by minimizing energy. I'm just going to skip over that one for now. This is the one that I was actually speaking of. The pop vault, or the vertical wall run, or the wall climb, they all work on the same principle. The force of friction must be greater than or equal to the force of the wall run step. So this is actually one of the ones that learning this changed my technique, and as all professors here have seen, I was able to pull off a really big wall run without any shoes on because of the fact that I changed my technique on this so significantly. So to show a wall run, oh god, see, this is bad. This is why you need power. Thank you. Also, okay, so actually have those of you doing this wall run. Okay, so here we have a wall that is, at last measure, I believe it's 12 foot 4 inches tall. So the concept of the wall run is that you accelerate towards the wall, you leap off the ground at this point, hit the wall, and use that rebound to go straight upward.
It's probably, to me, one of the most impressive techniques in parkour. Among other things, just some of the stats on this is cool, are cool. Among them is the fact that in parkour, a lot of us believe that this step here is actually the primary step in this technique, but it turns out that that step is actually fairly small in comparison to the one that hits the ground here. The stomp on the ground here actually generated 2 Gs, or 2.3 Gs of acceleration for him. So, for those who don't understand physics, he essentially experienced 2.3 times his weight through one leg off of that jump. And then this step is closer to 1.5. But the way that this works is that the horizontal momentum is used to create a normal force, as we were talking about with the friction before. It creates the normal force in this direction out of the wall, which allows for there to be enough friction for his foot to push down and actually launch up the wall. Now, the way that I changed this was I realized, after analyzing it, which I should have realized it a lot earlier, is that the friction is a very pivotal point here. So there are 2 types of friction. There's kinetic friction and static friction. The coefficient of friction changes depending on the type of friction you're using. Static friction is always greater than kinetic friction. So I actually changed my method of running up walls by avoiding kicking the wall. Because if you kick the wall and you get even the slightest rebound into your foot, you'll switch to kinetic friction. Your foot will start to slide and then it's out of control, just like a car. When it starts to slide, it doesn't stop. So the way that I place my foot on the walls now is very different. I actually run at the wall, and even though I have a lot of momentum going at the wall, I try and gently put my right foot on the wall and then shove at a fairly gradual force. That actually increased my wall run by well over 6 inches, even after just the first time I did it. So this is one of those really cool techniques that I was really glad to learn new stuff about it. One of the other interesting things about this is there are 2 different ways to do a wall run. A lot of people think one is inferior to the other, and I used to be one of those people. So there's a 2-step wall run and there's a 1-step wall run. I used to think the 2-step wall run was inferior because you can't get any traction on the foot and yada yada yada. It turns out, let's see which. If you actually look at this graph, it shows the effects of this wall run, and specifically I want you to look at this one here as its acceleration. Now, acceleration due to gravity is 9.8. So as he's flying upward, you'll see that he actually reaches almost 9.8. And then it drops to 9.8 at this point. This almost here is strangely enough due to his hand right here. And even when I told him this, he said, my hand doesn't do anything, though. It does. And actually, after realizing this, I started to feel that it did something. Your hand actually does help you defy gravity, for lack of a better word. It holds you up a little bit longer and helps you accelerate a little higher. So what was really interesting was to see this and then compare it with someone who does a 2-step wall run. So many mics. So many techniques that I've seen with names.
So do you practice both the 1-step and 2-step wall run?
No, not usually. Most people practice just one. They get comfortable with one. And a lot of people don't think 2-step works. And I was in that camp until I saw this. We have here a graph for his wall run. And you see here the exact same see, where right here defies that point right before dropping down. And if you watch closely frame by frame, you actually see that that point where he defies it is because his hand does almost nothing on this wall. It actually comes off here before he's even gotten any height. His second foot, the right foot, touches and pushes. His other hand is actually now back behind him. You can see it like a little fold there. So he actually gets the exact same effect off of the tip of his toe as Doza gets off of his hand. It turns out they're entirely equal techniques.
It looks like he's a lot further back.
Yeah, that is not a consistency that he has. He doesn't always end up further back, and sometimes we end up further back too, even with the. It's just a matter of how you impart your force on the ball in the first place.
Aligning myself again.
Okay, so, talking. The cat. The cat is cool. The cat was one of the things that when I started looking at the physics of it, I just thought it was a pretty concept. So you have the arrow here. This arrow represents the normal force where his hands are. And then you have the gravitational force on his feet, his mass and the gravitation, which is trying to push him downward. It's trying to push his feet downward. It's also trying to holding his hand down to the wall. You have the frictional force keeping his hand on the wall, and you have the frictional force keeping his feet on the wall. And you get that frictional force on the feet because of the small amount of rotation, the torque from the hands to the body that go into the feet by having a center of mass out in front of the feet here. So this is a really interesting technique to me because of the fact that you have all of these forces that have to remain in balance perfectly in order for you to maintain this technique. It's called cat. I'm going to go back to the cat because I want to show you the video, but I don't want to plug it and plug it back in. Landing. Landing is the act of ending a fall or flight, either to come to a complete stop or to transition into further movements. I like defining words that I've never had to define before. Combinations of movement made for quick changes in ideal motions to maintain momentum. A more difficult level of parkour, but a very necessary practice for efficiency. I'm almost there. I'm almost to a really cool spot. Okay, so we have here a very good example of a cat first. Go over that for a second. This is a cat. So what's interesting here is it actually matches something that we'll talk about really quickly, which is the precision landing. The idea is that the feet actually extend in the exact same direction as the parabolic, which is kind of interesting. But at all times, the center of mass is actually above that point. And as a result, in the cat, for instance, your center of mass is not coming directly into the feet, so not all the force goes into the feet. They're allowed to slip a little bit, which makes the dampening a little bit more possible. And when in the cat position, which we discussed. To look at some combinations. So, what we have here is common precision.
It's one of the few moves of parkour that I cannot do to save my life. Essentially, how it works is you're combining the idea of Kong with the idea of precision on an equal level. It's almost like a cat pass. Some people actually refer to this as a cat pass as well. I usually refer to a cat pass from starting with the feet at the same level, but anyway, arguably either way. This is actually what I consider to be one of the more impressive techniques so far as the amount of skill necessary to pull these off. There's a lot of things working in conjunction. You have to have the upper body strength, you have to have the lower body strength, and you have to have very good technique in order to do these. Also, just as an aside, to show you essentially how this program works, the program has you actually mark individual points on the body at every frame of the video, and it calculates the center of mass from the ratios of the weights of those parts of the body.
Parkour roll. Parkour roll is awesome. Okay, common misconceptions and initial observations. This is commonly stated in parkour. Parkour roll converts downward momentum into forward momentum. Physicists in the room should know that doesn't make any sense. Sadly, even though the physicists kind of do parkour, I never caught on to that until I was doing research. It doesn't make any sense. Down momentum is independent of forward momentum. You can't convert one into the other, not at least by the way that you're doing it. And the other common misconception is that it spreads the impact over a greater surface area. Some initial observations. Seems the x directional velocity is maintained, and the maximum initial x direction velocity is ideal. So that is to say that the more you jump out, the better your roll will be. Wrong. These were the assumptions I made at the beginning when I was starting the research, and I expected to see them. I was very wrong, and I was shocked when I was wrong. Because I have an ego, I guess. So, why are they wrong? Vertical momentum is not transferred to horizontal. Momentum in the y direction is completely independent of acceleration. Vertical momentum is entirely damped by the rolling process. Impact is not spread over a larger surface area in this case. For impact to be spread over a larger surface area, the larger area must be in contact with the ground at the same time. The surface area is, in fact, less in many cases during the roll because there are points of your body that are smaller than your feet that are touching the ground at any one point in time. That's still your entire body's weight on a smaller area than your feet, so it's not actually spreading the surface area, at least, again, not the way that you can do it. More questions. X-directional velocity is not perfectly maintained. Analysis shows some velocity in the rolling process, and the horizontal speed is supplemented by proper technique to push the body forward. Maximum x-directional momentum can cause issues with both friction and lack of control. Ideal angle of impact to begin the roll is actually approximately 45 to 40 degrees. This means that the x-directional initial velocity is actually based on the height in which you are falling. The female parkour roll. This was a major problem. Women tend to have greater difficulty learning to execute a roll versus men. This was found to be a result of the lower center of mass. Because of the lower center of mass, when they try to roll, they actually have to jump over about 6 inches more of their body, and they end up flopping on their back a lot. Thanks to Hannah, a girl in Japan who I contacted because I found out she had a really good roll, I was able to find one possible solution to this problem. So I need to switch over to show you some weird stuff. So when I initially started looking at how the roll worked, I expected to see that x-directional velocity remained the same. It's sort of the idea of why you're doing the roll. And I was really confused when I got the results that I got. So, starting with any one of these. Here is Mike doing a roll. Very standard roll. This is exactly what it looks like. Rolling on concrete. Doesn't want to make it hard on the inside. Okay. This is his x-directional velocity. Note the sine wave. I was shocked to see a sine wave. I was very confused to see a sine wave. And it turns out when I analyzed everyone's roll, the same sine wave came up with nearly the same, word's gone. No, not a frequency. Nearly the same frequency. It actually seems that the frequency changes based on their height. So I found this and I was like, why is that there? And I spent 3 days just mulling over it every time I was driving somewhere in school and sitting in class, not paying attention to geometry, trying to figure out why the heck there's a sine wave in the x-directional motion. No, this is not a sine wave in the rotational motion. This is not a rotational sine wave that I would have expected. But instead, this is actually a lateral sine wave, so the velocity is actually doing this as the person rolls forward. So, upon closer inspection, I came to a conclusion that this is actually due to an extension and compression of the body. So, at the point of impact, you curl a little to take some of the power, you extend, which extending slows your speed because it slows your roll. You crunch, which speeds up your roll, speeds up your speed. You extend, you crunch, you extend, and that creates sine wave. Now I thought that was all well and good. Of course I was wrong. I was wrong a lot when it came to the roll. The roll was the bane of my existence. And I got things like this, where when I rolled, so when I rolled, I got something a little bit odd. I got the sine wave, but I got the sine wave that does this. It goes thump. And I couldn't figure out why that was. And that bothered me for a while. You also see this sine wave, but we'll discuss that more later. So I couldn't figure out why that was there. But I just sort of ignored it because I'm a terrible physicist. And I just assumed that it was some anomaly or some mistake I made in my roll that caused that. I turned out to be wrong. So when Hannah, I contacted her to work on the girl roll, I didn't actually expect to get quite so much information out of her roll. Hannah is a girl in Japan who has a very good roll for a girl. And that's not a sexist thing, it's just good. So she has this really interesting roll. And when I tried to graph her roll, I realized that her frequency was increasing. And when I tried to figure out why her frequency was increasing, I went, oh, well, of course. If you look closely,
you see that in order to avoid having to roll over that 6 extra inches of center of mass, she actually twists her body to the side so that the rotation is about a different axis. You see her feet are actually on the opposite side of her from the now. And this actually fixes the girl roll. And I was like, well, because she's changing her axis, she has a smaller R, so you expect that her sine wave would actually change frequency. And I thought that for a good hour, and then I realized how stupid that was because this is an x-directional sine wave, it is not rotational, as I just said a few minutes ago. If it was rotational, you would expect it to change frequency because of the turning, but that's not the case. So I started to try and analyze the roll further and figure out why this was, and I realized that there's something else in the roll. There's the fact that you're top-headed. So in the middle of the roll, it's right now, probably not going to light. In the middle of the roll, from here, your center of mass is way up here, the ground is down here. And you're rolling around your hands, so your center of mass is above the circle. So if you imagine trying to roll a ball that has ice frozen in one half of it, it will go so you'll get a sine wave in the x direction. So I concluded that that is where it came from. And then I realized that if you watch the person roll, unfortunately that sine wave has a very different frequency. It's actually much lower than the frequencies you see here. Obviously, the roll drove me nuts. I spent months on the roll alone. After analyzing her roll, analyzing about 7 other people's rolls, especially like a few of mine, trying to figure them out, I finally came to a conclusion. You did it. Here is a pretty equation, not pretty at all. I also have like terms that I don't know why they did that, but there's like terms there. Add 3.1 to 3.5. Okay, so you have this equation. You notice there's 3 sine waves there. You also would notice if I had my computer hooked up that that is actually exactly the sine wave of my roll to the T. And thus, that's how I roll. I plan to make a t-shirt out of this. I'll have a graph, I'll have an equation, and I'll have, that's how I roll. So, it is made up of 3 sine waves acting in conjunction with each other. You have the orange sine wave, which is the top heaviness of the roll, which is here. You have the green, which is actually due to frictional forces. Now, on most people, you actually won't see the same sort of destructive interference as you see at the end of mine, and that's actually because their frictional forces are actually in time with their rotation. You look at it really closely and go frame by frame and spend way too many hours on it. So, the green is the frictional forces of my body hitting the ground and actually getting friction. So as you come here, this is where my body is hitting the ground and something picks up, and I'm off the ground for a little bit, and then I'm on the ground and off the ground, etc. The red is the compression and extension that I saw originally. So it turns out when you combine all these, you get this interference pattern, and that's how I roll. So, the Parkour roll. Comparing it with other landing methods, I was going to pull up a pretty graph, but unfortunately, I don't have it on this computer. So I'm just going to discuss it. I did analysis on it for 2 people who were different from each other, which is why I didn't put it in here. I was going to actually make another one with just me doing all options. But essentially what I ended up coming out to, after taking the integrals of the curves of their motion, I actually was able to find that a person who is untrained, who jumps from a height of, I believe it was 5'3",
jumped down, landed straight-legged, it looked horribly painful. Another person jumped up and actually went into the air and came down. He ended up jumping, her jump was 2/3 the height of his jump. Despite that, in the end, the amount of impact or impulse, whichever it is, I keep mixing these up. The amount of impact was half on him, even though he jumped higher and weighed more. Simply because of the fact that the roll, the way that the roll works is the amount of force that is applied is laid out over a greater amount of time. So the deceleration is slower, at least in the y direction. The x direction is not maintained, it's actually called a sine wave, but it almost maintains. So that's the roll. Final thoughts and further study. Tic-tacs, method of kicking off. These are things I wish I had time to get to, but honestly I spent months on the roll. Tic-tacs is a method of kicking off the surface to change direction or gain height. Horizontal wall runs. It's arguably a sister technique to tic-tac. It's also very similar to the vertical wall run. It works on the same principles, running up a wall, getting enough friction in order to do a movement. Dive rolls. Dive rolls are really fun. You go over an object by diving over it, and then you use the roll to come out of the dive without having to put your feet down first. Turnbulls, underbars, cliches. I don't know if that's like cliches. Various movements used to overcome areas with bar work, railings, moving over and under and through such objects. Really what it comes down to is there are way too many parkour techniques. I do in fact actually plan to continue this research, even though I graduate this semester. I plan to continue this research. I actually started a YouTube account called Parkour Science, where I will be posting videos on individual techniques and really doing in-depth analysis of each individual technique, both for the physics aspect of it and for the parkour aspect of it for tutorial reasons, to help people understand how things work. Quick side note. Free running is another thing that could be delved into.
How do you get tired of parkour, or is that possible?
So I did one example of this, just for the sake of having an example. I'd also just like to say, to give you an idea of how much time I spent doing this, each frame requires 10 data points. I actually did the math, and by the end of the semester, I had clicked a mouse over 50,000 times to get this data. 50,000 data points in total for all of my data. Okay, so delve into free running. We get to see some interesting ideas of free running. So here we have a big front flip into a roll, straight into a side flip. It's a pretty neat thing to look at, but one of the things that's kind of interesting about this, I'm just going to plot this, it's easier. If you actually look at the Y components, this is something that you would really expect to have, and wow, do I hope this works out when I do it, because otherwise it would be kind of. So, if you start from the point that he takes off here, which looks like go to the point before it lands. I can fit a curve back, and please work. So don't look like you do. That's pretty darn good. You get the equation that we started with right at the beginning. X equals, well, y. Y equals y naught. This is where you started from, 0.7 meters up. Whatever. V naught, this is where you start. Oh, that's okay. So, V naught, and then you get 1/2 G, which G is approximately 9.8. So, pretty close, right? So, that shows that actually independent of rotational motion, you still get your parabolic, which shows the normal sort of ballistic equations that you expect to see. The rotational inertia is actually independent. Also, for the sake of arguing with myself, because I had this conversation with you, which is sort of, it's a common argument that front flips are not parkour, and they cannot be parkour because they're inefficient motion. I had said that I found proof that the front flip could be parkour. Now, there are very few instances where this is true, but what I actually found in here that shows that it's false, especially in this instance, is actually not the height that it jumps. The height he jumps is equal to anyone else who would run and jump off of this object. Most people jump up slightly when they jump off. It actually turns out that he actually puts 2 G's of force into this jump, whereas a normal person has no effort into doing this little leap. So the amount of force he actually has to put in to get this rotation as clean as he has it is actually fairly significant, making it fairly efficient.
Last switch. I thought it was going to be business. Okay.
Special thanks. Dr. Ware, there's a long list. These are all the people who helped me with the research, obviously Dr. Ware, and various people who stood in to be subjects for me to study or